Hello students. In this video, I would like to discuss a very interesting topic called infinite series from chapter 12 of our textbook. Now, this topic has some connection with infinite sequences. So let me remind you what we have done in infinite sequences. We define what do we mean by infinite sequences. It's a list of numbers or spatial objects, and then we realize that dealing with sequences could be kind of tricky because sequences may generated by random entries. So general term computation of sequence may or may not be possible. So we focus our attention on a very special type of sequence called geometric sequence. This sequence was constructed using two numbers a and r, right? And we have seen some application of this particular sequence in the past, right? So in fact, in the last lecture we study about annuity. All right, so now let's focus our attention on this very new topic. We call it infinite series. As I mentioned, it has a connection with infinite sequence. So let's begin our discussion with by recalling a definition of infinite sequence. All right, a list of number of the form a1, a2, a3 all the way till infinity is called a sequence. All right, so list of number is called sequence. Now the question is, what is infinite series then? Let me tell you, the definition is very simple. If you add all these infinitely many terms of your infinite sequence, then the expression that result by this addition is called infinite series. All right, so an expression obtained by adding all terms of your infinite sequence is called infinite series. All right, so you are adding infinitely many terms and the final result will be something, right? So you are adding infinitely many numbers. The question is, will the final result be a numerical value or will it be infinity or negative infinity, because you are adding infinitely many terms. All right, mathematical notation, well, as I said, it's a very simple definition: addition of all these terms of your sequence a1 plus a2 plus all the way till infinite term. Instead of writing series in that long form, we adopt this notation sigma, where sigma stands for sum running from n to n equal to 1 to infinity of an. All right, this means plug n equal to 1, you get the first term, and then add plug n equal to 2, you get the second term, n equal to 3, you get the third term, and so on so forth, and then you add them. Again, sigma stands for the summation. All right, okay, now here is the genuine question that we have in our mind, that is it possible that sum of these infinitely many terms result into a finite number? All right, again, very simple question, that you are adding infinitely many terms. Is it ever possible that result of this infinite sum is going to be one particular finite number? Well, if you say it is not possible, then there is nothing surprising, right? You are adding infinitely many terms and result more or less, because it's an infinite sum, we feel like the result will be infinity. It would surprise us if the answer to this question is yes, right? Indeed, answer to this question is yes. All right, so adding infinitely many terms sometime result into a finite number. Okay, and we are going to systematically introduce this idea. Okay, so adding infinitely many terms may result into a finite number as a final outcome. The question is, if we get finite number as an outcome of infinite sum, then how do we obtain that infinite term? I want you to recall, what is infinity? Infinity is not a number. Infinity is just a concept. Infinity really is a tedious symbol that represent a huge quantity with no known value. All right, so it's just a concept, right? Infinity is not a real number. It's just a concept representing huge quantity. So in reality, we don't even know what do we mean by add infinitely many terms, because infinity is not a number. Like for example, if I ask you to add 100 term, we know 100 it's a finite quantity. You can add first 100 term and result will be a finite number for sure. But since I don't know the exact value of infinity, we don't know how to add infinitely many numbers. The question is, have we handled this symbol before? Well, think about it. If you um, if you recall a little bit, you will realize that in improper integration, we found a way to deal with this symbol infinity, right? If you remember, I made this comment when we discussed improper integral that I am going to recall this result in chapter 12. This is the time to recall that result. Understand how we handle the symbol. If you want to find integral of f of x over the region a to infinity, our standard standard method was, instead of, because infinity is a symbol and fundamental theorem of calculus is not applicable for symbol, I would pick a variable that sits between a and infinity, and I would integrate my function from a to t. This is a definite integral. T is a variable, right? Fundamental theorem of calculus is valid for this particular expression. My final answer will be in terms of variable t. Then I would like to know that what happened with this definite integral as t goes to infinity. Alright, because infinity is a symbol only, we can only make a prediction that what's gonna happen with this definite integral as t increases without bound. Alright, so the similar type of approach can be designed to understand sum of infinitely many terms of your sequence or infinite series. Okay, so as I said, we can use the similar approach here. Instead of adding infinitely many terms, I would add, let's say, first n terms, and then I will try to compute its limit as n goes to infinity. If this limit exists as a real number, then I'm going to use the wording similar to the one that we have used in case of that improper integral. Series converges. Alright, if this limit does not exist, I would declare that series is divergent. Anyway, we will go there. What is important here is we had a name for this particular integral. It was a definite integral, right? We don't have a name for sum of first n terms. Let's give it a name first. Okay, I'm going to call sum of first n terms nth partial sum. Okay, so the sum of first n terms of series is called nth partial sum, and notation is S sub n, where S stands for sum, n stands for number of terms that we are going to add. We have used this symbol earlier for sum of first n terms of the geometric sequence. Alright, it's the same thing. Now we are giving it a name, official name, because we are going to be finding its limit as n goes to infinity to understand if the series, if sum of infinitely many terms result into finite number or not. Alright, so here is nth partial sum notation. S sub n is sum of first capital N terms. In sigma notation, it's a sigma I running from 1 to n, ai, plug I equal to 1, 2, 3 all the way up to n and add the result. Alright, again sigma stands for summation. Okay, alright, let's try to see few trivial examples. few computational examples. All right. Compute first 5 partial sums of this series summation n running from 1 to infinity 3n plus 2. Okay. Again, I would like to calculate first 5 partial sums. So I would like to calculate S1, S2, S3, S4, S5. What is S1? Sum of first one term. S2, sum of first two terms. S3, sum of first three terms. S4, sum of first four terms. And finally S5, sum of first five terms. As I said, these examples are trivial. There is no trick. So let's try to understand this. S1 is sum of first one term, meaning first term itself. 3 times 1 plus 2, I get 5. S2, sum of first two terms, A1 plus A2. 3 times 1 plus 2 plus 3 times 2 plus 2. This is the first term, this is the second term. Simplify it, get 5 plus 8 equal to 13. Compute S3, sum of first three terms, A1 plus A2 plus A3. Plug n equal to 1, 2 and 3. And then add the results together. I get 5 plus 8 plus 11. Result into 24. S4 likewise, sum of first four terms. Obviously I don't want to write that long formula, so I use sigma notation. Okay. 3 times 1 plus 2, 3 times 2 plus 2, 3 times 3 plus 2, 3 times 4 plus 2. Add all these numbers, the result is 35. And sum of first five terms. Fifth partial sum is summation I running from 1 to n, 1 to 5 of ai. Plug n equal to 1, 2, 3, 4, 5 in an and then add them together. Alright. If you do that, you will get 54. Alright. So we have first, second, third, fourth and fifth partial sum for this infinite series. Okay. Alright. The next question is a question about convergence and divergence. I already mentioned this thing earlier as well. Suppose you have given an infinite series that resulted by adding infinitely many terms of some sequence. Right? So suppose S is A1 plus A2 plus all the way till infinite term, or sigma n running from 1 to infinity an. Suppose this is the infinite series that is given to you. And let's say I consider nth partial sum, which is sum of first capital N terms. Alright. When can I say the series is convergent? Well, if limit of the nth partial sum exists as a real number as n goes to infinity, then the series is convergent, otherwise it is divergent. Okay. So here is the first first remark. Limit n goes to infinity of sum of first n term. If this limit is finite number, then infinite series is convergent. If this limit does not exist, then we declare that infinite series is divergent. Okay. All right. Now, what we would like to complete this video with one very simple remark. Remember, sequences themselves could be tedious because computation of general term may or may not be that easy. Alright, and now we are adding infinitely many terms. Series may be in a very tricky form. Alright, computation of limit, computation of nth partial sum in general form, it is very tricky for many series. And if the series is random, then most likely it is impossible to come up with the general form of sum of first n terms. Alright, so if we can't get general form of sum of first n terms, then we will have trouble computing limit. Alright, and that is the reason why I mention here that computation of this limit could be very difficult to obtain. Alright, many times it is impossible to obtain sum of first n terms in its most general form. Alright, so this is the reason why we don't want to get into the general theory of infinite series. We would like to focus our attention on a very special type of series that we call geometric series. Yes, this is the series that is obtained by adding infinitely many terms of geometric sequence. Alright, so in next video we are going to focus our attention on geometric series, and we will talk about their convergence and divergence criteria. But for now, understand that infinite series is an expression obtained by adding infinitely many terms of any general sequence. Computation of some designing definition was very easy for determining convergence and divergence of a partial of infinite series. However, computation of nth partial sum in general, in terms of in terms of n, could be tedious or could be extremely difficult or even impossible in many cases if your series has random entries. And that is one reason why this way is not a preferred way to handle series. All right, some series, some special series can be handled using this way. Not all of them can be handled using this idea. This is the idea that works to prove important results and theory involved with infinite series. Unfortunately, practically this is slightly tricky. All right, so we are not going to use it. The point is, we will be focusing on, we will try to keep the things as simple as possible, and we will focus our attention on geometric series.